Hello! In this video, we are going to prove the following theorem. Every finite set has a unique number of elements. Okay, before we get into the proof, let's get some context. To start, we're going to say that the natural numbers includes 0. And the set of positive integers refers to the natural numbers not including 0. And for each natural number n, we are going to call the set IN the set of the first n positive integers. In other words, we're going to say that IN is the set of all positive integers I, such that I is less than or equal to n. And also, what does it mean for a set to be finite? Well, we're going to say that A is finite if there exists a natural number n such that we have a bijection from IN to A. And for shorthand, we're going to write this statement as this. Now, let's actually get into the proof. We're first going to prove that for all natural numbers n and m, if there is a bijection from IN to IM, then n is equal to m. And to prove this, we're going to use mathematical induction on n. So let's start with the base case. Now in the base case, we're trying to prove that this statement is true in the case where n is equal to 0. Okay, so then what is this statement saying in the case where n is equal to 0? Well, really, if we substitute n for 0, we're trying to prove that for all natural numbers m, if there's a bijection from I0 to IM, then m is equal to 0. So really, this is what we're trying to prove in the base case. And since we're trying to prove a statement about every natural number, give me an arbitrary natural number. I'll call it m. And with this arbitrary natural number m, we're trying to prove if this is true, then this is true. So let's suppose that there is a bijection from I0 to IM. Now really, I0 is precisely this set where we replace n with 0. So really, I0 is the set of all positive integers I, such that I is less than or equal to 0. But wait a minute, there are no positive integers less than or equal to 0, so really, I0 is the empty set. So what this really means is that there's a bijection from the empty set to IM. And we're going to call that bijection F. Now our whole goal is to deduce that m is equal to 0. So let's assume for a contradiction that m is not equal to 0. What happens if m is not equal to 0? Well, we know that m is a natural number and m is not equal to 0. But really, the set of all natural numbers that are not equal to 0 is equivalent to the set of positive integers. And since m is a positive integer, it follows that m is an element of the set of the first n positive integers. And also, since f is bijective, it follows that f is surjective. So what that means is, for every element b in IM, there is an element a in the empty set such that f of a is equal to b. So, since m is an element of IM, there is some element p in the empty set such that f of p is equal to m. But wait a minute, the empty set has no elements, so we've reached a contradiction. Our assumption that m is not equal to 0 led us to a contradiction, so we must instead have that n is equal to 0. So we have proven that m is equal to 0, which is what we wanted. So we have proven this statement, which means we've completed the base case. Now let's move on to the induction step. Now, in the induction step, we give ourselves an arbitrary natural number n, where this statement is true for that natural number n. So really, substituting n in this statement for this natural number m, what we're supposing here is that for all natural numbers m, if there's a bijection from in to im, then n is equal to m. And the whole goal of the induction step is to prove that this is also true for n plus 1. So really, this is the statement we're trying to prove. And we're trying to prove a statement about all natural numbers, so give me an arbitrary natural number. I'll call it n. And with this arbitrary natural number m, we're trying to prove if this is true, then this is true. So let's suppose that this is true. And our whole goal is to deduce that n plus 1 is equal to n. Now, since there's a bijection from in plus 1 to im, what this means is we can choose some bijection f from in plus 1 to im. Now, n plus 1 is not only a natural number, but n plus 1 is also a positive integer. And since n plus 1 is a positive integer, it follows that n plus 1 is an element of the set of the first n plus 1 positive integers. So n plus 1 is an element of in plus 1. And since n plus 1 is an element of the domain of f, it follows that f has a functional value at n plus 1. We can say, for instance, let k equal f of n plus 1. And note that f of n plus 1 is an output value of the function f, so really, f of n plus 1 is an element of im. So really, k is an element of im. Now really, im is really this set, where we replace n with m. So what this really means is that k is less than or equal to m. But not only that, k is a positive integer. So really, k is greater than 0. But not only is k greater than 0, m is also greater than 0. And to say m is greater than 0 means that m is a natural number that is greater than 0, or in other words, m is a positive integer. And since m is a positive integer, it follows that m is an element of the first m positive integers. So really, m is an element of im. And now, we can use the fact that f is surjective. What that means is, well, since m is an element of im, there is some element j in in plus 1, such that f of j is equal to n. Okay, now I would like to write some notes up here before we move on. First of all, we have a bijection, f, from in plus 1 to im. And we've identified some functional values of f. One is that f of n plus 1 is equal to k. And another is that f of j is equal to n. Now, remember, our whole goal has been to deduce that n plus 1 is equal to n. And we somehow need to implement our induction hypothesis, which is the fact that we know that this statement is true. And the way that we can use this fact is, instead of trying to prove n plus 1 is equal to m, let's prove that n is equal to m minus 1. The reason why is, well, because m is a positive integer, surely m minus 1 is a natural number. And this statement works for every natural number, so it must work for the natural number m minus 1. So if we substitute this for n minus 1, well, we know that if there is a bijection from in to im minus 1, then n is equal to n minus 1. So, if we can find a bijection from in to im minus 1, it will follow that n is equal to n minus 1 by this statement. And since n is equal to n minus 1, we have that n plus 1 is equal to n, which is exactly what we want to prove. So all we have to do now is find a bijection from in to im minus 1. We claim that there's a bijection from in to im minus 1. And we're going to define what that bijection is right now. So, we define a function g with domain in. Now, to establish a bijection from in to im minus 1, we're going to use our bijection f from in plus 1 to im. Now, visually, we can think of our bijection f like this. Right, so visually speaking, we can think of our function f like this, right? Each element of in plus 1 is assigned to an element in in, and we have a one-to-one correspondence between the two sets. Now, to establish a bijection from in to im minus 1, well, let's cut off n plus 1, because we're only concerned with the first n positive integers. Now, if we give ourselves an arbitrary positive integer I in in, well, if I is not equal to j, then all we'd have to do is send I to f of I. So just like that. So then the only other possibility we need to think about is if I is equal to j. What do we do for I equals j? Well, instead of sending I to n, we'll just send I to k, because nothing has been assigned to k yet. Right, so just like that. So visually speaking, from our function f, we have been able to establish what we suspect to be a bijection from in to im minus 1. Now, granted, this visualization makes us assume that j is not equal to n plus 1. So then what if j is equal to n plus 1? Well, visually speaking, here's how this would change. In the case where j is equal to n plus 1, well, I'm going to write j is equal to n plus 1, and therefore k is equal to m. Now remember, g has domain in, so I'm just going to cut off n plus 1. Now let's make sure that g is suspected to be a bijection from in to im minus 1. Well, let's see. Give me an arbitrary positive integer I in in. If I is not equal to j, we'll assign g of I to f of I. So, no positive integer between 1 and n is equal to j in this case. So, g of I will be assigned to f of I for every positive integer we have here. So as you can see, all elements in in are assigned to elements in im minus 1. And it appears we have a one-to-one correspondence between these two sets. So yeah, it seems like we expect g to be a bijection from in to im minus 1. So now, we're actually going to prove that g is a bijection from in to im minus 1. And to prove g is a bijection from in to im minus 1, we're first going to prove that g is a function from in to im minus 1. And to prove this, we're going to show that for every element I in in, g of I is an element of im minus 1. And since we're trying to prove this statement about all elements of in, give me an arbitrary element of in. I'll call it I. And our goal is to prove that g of I is an element of im minus 1. Now, since I is an element of in, it follows that I must be an element of in plus 1. Now, I is an element of in plus 1, but I is not equal to n plus 1 because n plus 1 is not an element of in. So, we have that I and n plus 1 are both elements of in plus 1, but they're not equal to each other. Well, since f is injective, we know that f of I is not equal to f of n plus 1. Now, we're going to consider two cases. Either I is equal to j or I is not equal to j. And in either case, we're going to prove that g of I is an element of in minus 1. Let's start with the first case where I is equal to j. Now in the case where I is equal to j, we know that g of I will be assigned to k. And k is equal to f of n plus 1, but as we stated up here, f of n plus 1 is not equal to f of I. And since I is equal to j, f of I is equal to f of j. And we know that f of j is equal to n. So, what we see here is that g of I is not equal to n. Now, since g of I is equal to k, and k is an element of im, surely g of I is an element of im. So, g of I is an element of im, but not equal to m. So, g of I is an element of im minus 1, which is exactly what we wanted to prove. So, this completes the case where I is equal to j. Now let's move on to the case where I is not equal to j. Now, in the case where I is not equal to j, we have that since f is injective, that f of I is not equal to f of j. Okay, now check this out. Since I is not equal to j, we know that g of I will be assigned to f of I. And we also know that f of I is not equal to f of j. And we know that f of j is equal to n. So we see that g of I is not equal to n. So really, we know that since g of I is equal to f of I, and f of I is an element of im, we have that g of I is an element of im. Therefore, g of I is an element of im, but not equal to n. Putting those two together, we must have that g of I is an element of im minus 1. So, we have proven that g of I is an element of im minus 1, which is exactly what we wanted. And so putting this all together, since I was an arbitrary element of in, we have that for all elements I and in, g of I is an element of im minus 1. And that is exactly what we wanted to prove. So we have proven that g is a function from in to im minus 1. So now that we know g is a function from in to im minus 1, now we want to show that g is a bijection from in to im minus 1. So really, we're going to show that g is both injective and surjective. Let's start out by showing that g is injective. And to show g is injective, what we're going to do is we're going to show that for every two elements, I1 and I2 in in, if I1 is not equal to I2, then g of I1 is not equal to g of I2. So to prove that, give me two arbitrary elements, I1 and I2 of in, and suppose I1 is not equal to I2. And our whole goal is to deduce that g of I1 is not equal to g of I2. Now, since I1 and I2 are elements of in, surely they are both elements of in plus 1, but not equal to n plus 1. And now, using the fact that f is injective, we know that since I1 is not equal to I2, that f of I1 is not equal to f of I2. Since I1 is not equal to n plus 1, f of I1 is not equal to n plus 1. Since I2 is not equal to n plus 1, f of I2 is not equal to n plus 1. Now, at this point, we are going to consider three cases. And in all three cases, we're going to prove that g of I1 is not equal to g of I2. And that will prove g is injective. So, the three cases are either I1 equals j, I2 equals j, or both I1 and I2 are not equal to j. Let's start with a case where I1 is equal to j. Now, since I1 is equal to j, and I1 is not equal to I2, we have that I2 is not equal to j. Since I1 is equal to j, we have that g of I1 is equal to k. And k is equal to f of n plus 1. And from what we have above, f of n plus 1 is not equal to f of I2. And since I2 is not equal to j, this means that g of I2 is equal to f of I2. So what we've established here is that g of I1 is not equal to g of I2, which is exactly what we wanted to show. So this completes case 1. Now let's move on to case 2, where I2 is equal to j. Now, since I2 is equal to j and I1 is not equal to I2, we have that I1 is not equal to j. Since I2 is equal to j, we have that g of I2 is equal to k. And k is equal to f of n plus 1. And from what we have above, f of n plus 1 is not equal to f of I1. And since I1 is not equal to j, we have that g of I1 is equal to f of I1. So, from here, we see that g of I1 is not equal to g of I2. And that's exactly what we wanted to show, so this completes case 2. Now let's move on to our final case, where I1 and I2 are both not equal to j. Now, since I1 is not equal to j, we have that g of I1 is equal to f of I1. And from what we have above, f of I1 is not equal to f of I2. And since I2 is not equal to j, we have that g of I2 is equal to f of I2. So we see from here that g of I1 is not equal to g of I2, which is again exactly what we wanted to show. So, in all three cases, we have g of I1 is not equal to g of I2. So, we have proven that g is injective. So now, we're going to show that g is surjective. What does this mean? Well, what this means is we're trying to show that for every element q in in minus 1, there is an element t in in such that g of t is equal to q. So we're trying to prove a statement about every element in in minus 1, so give me an arbitrary element of in minus 1. I'll call it q. And the whole goal is to show that there is an element t in in such that g of t is equal to q. Okay, now to start, since q is an element of in minus 1, it follows that q is also an element of in, but not equal to m. So, since q is an element of in, and f is surjective, we know that there is an element p in in plus 1 such that f of p is equal to q. Now, we're going to break this up into two cases. Either q is equal to k, or q is not equal to k. And what we're going to do is we're going to prove in either case, there is an element t in in such that g of t is equal to q. Let's start with case 1, where q is equal to k. The claim in this case is that g of j is equal to q. And that makes sense because if we have j equal to j, then g of j would equal k, which is equal to q. But in order for that to work, we would need to show that j is an element of the domain of g, right? Because at this point, we only know that j is an element of in plus 1. We must show that j is an element of in. We know that f of j is equal to m. And m is not equal to q. And q is equal to k. And k is equal to f of n plus 1. So f of j is not equal to f of n plus 1. And this implies that j is not equal to n plus 1. Why? Because we know that if j equals n plus 1, then f of j equals f of n plus 1. The contrapositive tells us if f of j is not equal to f of n plus 1, then j is not equal to n plus 1. So, since j is an element of in plus 1, but not equal to n plus 1, it follows that j must be an element of in. And now, since j is an element of in, g has a functional value at j. And so sending j into the function g, since j is equal to j, we have that g of j is equal to k. And k is equal to q. So what do we see here? There is an element t in in such that g of t is equal to q, namely j. So this completes case 1. Now we're going to move on to case 2, where q is not equal to k. Now our claim in this case is that g of p is equal to q. And in order to show that, we have to show that p is an element of the domain of g. Right? We need to show that p is an element of in, because that's the only way that we could send p into the function g. The other thing is, in order for g of p to equal q, we would have to show that g of p is equal to f of p, which is equal to q. Right? Because that would be a valid chain of equalities to do that. And to show that, it suffices to show two things. We're going to show that both p is not equal to n plus 1 and p is not equal to j. And to see how that comes together, first of all, we know that f of p is equal to q. And we know that q is not equal to k, and k is equal to f of n plus 1. So f of p is not equal to f of n plus 1. And remember, this implies that p is not equal to n plus 1. And next, to show that p is not equal to j, well, we know that again that f of p is equal to q, and q is not equal to m, and f of j is equal to m. So f of p is not equal to f of j. And remember, this tells us that p is not equal to j. So, we have that p is not equal to n plus 1, and p is not equal to j. Let's put this together. Since p is an element of in plus 1, but not equal to n plus 1, it follows that p must be an element of in. So we have that p is an element of in, and p is not equal to j. Well, when we send p into the function g, which we can since it's an element of in, we have that g of p is equal to f of p. And we know that f of p is equal to q. So g of p is equal to q. So what do we see here? Well, we have found an element t in in such that g of t is equal to q, namely p. So, no matter what case we have that there is an element t in in such that g of t is equal to q. Since q is an arbitrary element of in minus 1, we have that for all elements q in in minus 1, there is an element t in in such that g of t is equal to q. This proves that g is surjective. So really, we have shown that g is a function from in to in minus 1 that is both injective and surjective. So g is a bijection from in to in minus 1. And what this means is there exists a bijection from in to in minus 1. So we're going to write in squiggly in minus 1. And if we recall, way back to our induction hypothesis, it said that for all natural numbers m, if there is a bijection from in to im, then n is equal to n. Well, m minus 1 is a natural number, and there is a bijection from in to im minus 1. So our induction hypothesis tells us that n is equal to m minus 1. And so n plus 1 is equal to n. And this is exactly what we wanted to prove in the induction step. So this completes the induction step. Because we've proven both the base case and the induction step, we have proven precisely this statement. And now we're actually going to prove what the theorem says. And in proving this, we're going to be using some facts about this statement in general. It turns out, given sets A and B, if there is a bijection from A to B, then there's a bijection from B to A. And second, if there's a bijection from A to B, and there is a bijection from B to C, then there's a bijection from A to C. Okay, so now let's actually prove this statement. Since we're trying to prove a statement about every finite set, give me an arbitrary finite set. I'll call it A. Now, what does it mean for A to be a finite set? Well, by what we have here, what it means is that there is some natural number n such that we have a bijection from In to A. Now, our whole goal is to prove that A has a unique number of elements. Okay, but what do we mean by number of elements? Well, we can think of this number n as a number of elements in A. We essentially want to show that n is the only number of elements in A. How do we do that? Well, we got to prove that n uniquely satisfies this condition. How do we prove that n uniquely satisfies this condition? We want to show that every number that satisfies this condition is equal to n. Well, give me an arbitrary natural number, n prime, such that there is a bijection from In prime to A. And our goal to show that n is unique is to show that these two are equal. So, since there is a bijection from In prime to A, we know that by what we have here, there is a bijection from A to In prime. Also, since there's a bijection from In to A, and there's a bijection from A to In prime, it follows by the second fact that there is a bijection from In to In prime. And now, we can use the fact that we just proved, right? For all natural numbers n and m, if there's a bijection from In to Im, then n is equal to m. Well, n and n prime are both natural numbers, so we can substitute n here for n, substitute m for n prime. And we have that if there's a bijection from In to In prime, then n is equal to n prime. Well, as we have here, there is a bijection from In to In prime, so this statement tells us that n is equal to n prime. So, n is equal to n prime, which means we have proven that n uniquely satisfies this condition. In other words, n is the only number of elements in A. So, given A is a finite set, there is a unique number of elements in A. And so this completes the proof. So given a finite set A, there's a unique natural number n that satisfies this condition. This natural number n is what we will call the number of elements of A. So really what this is saying is, for each finite set A, we can assign it to a unique natural number n. And this natural number n we will call the cardinality of A, and we will denote it as follows. Just like that. And so yeah, that's pretty much it for this video.